Okay, hello everyone, welcome back. So we're ready for the second session, but before doing so, I just wanted to, as an oversight, I just wanted to mention that TAL is one unit of the mobility network. So the mobility network is a network of research centers and labs across the University of Toronto. And its vision is really to catalyze transformation in the ways mobility is achieved and how this results in a more equitable, sustainable, and prosperous future. So the mobility network is headed by Professor Eric Miller, my colleague here in the Department of Civil Engineering. And this event is co-sponsored and co-hosted by the mobility network. So, so the second session is concerned with analytics to improve rail performance. We have three presentations. As some of you may recall, back in the earlier in the year, about in February, we had a whole workshop focused on TAL's research in the area of rail analytics. So we're going to share some of the results. Here will be some extensions of the work that we presented earlier, and also some new research. So this is an active area of research of ours. So there are three presentations. The first presentation is by Aidan Grenville, and a quick word about Aidan. Aidan is graduated from the aerospace engineering major in the engineering science program at U of T this year. He actually worked with TAL over his final year of studies, completing both summer research and an undergrad thesis on the topic of understanding TTC subway delays using Wi-Fi traces. So again, another study that utilized Wi-Fi. So he now works for United Airlines in the operations strategy department, but he continues to use insights and methods he learned from the world of transportation analytics. So outside of work, Aidan loves everything and anything to do with the mountains, but being outdoors more generally as well. So Aidan, over to you.
Hi, everyone. Let me start the screen share. All right, so yes, thanks, Amer, for the introduction. And so I'll be talking today about analyzing TTC performance during service disruptions using Wi-Fi connection data, as mentioned. I'll breeze through the first part pretty quickly, just explaining how we kind of use this Wi-Fi connection data, as I know folks have heard about that a little bit already. So the TTC Wi-Fi network is operated in the stations. It's operated by BAI Communications, so thanks to them for partnering with us on this project, and it allows passengers to connect to a free service when they're in the stations. So what we can do is we can actually see device records of devices that associate and dissociate at a given station. And this allows us to create a journey mapping to understand how devices, which we use as a proxy for passengers, are moving through the system from the origin to destination and what stations they go through in many cases as well. So the question we asked earlier this year was what happens when the trains stop moving? And as we all know, TTC delays do happen. They're unfortunate, and they're not a particularly popular part of traveling on the TTC. So we wanted to see if we could better understand from a sort of device and therefore customer level viewpoint of how people are moving when the trains stop moving, rather than just looking at how the trains are stopping to move. So we used and created a delay record from the public public-facing delay logs, both on Twitter and via the email service. So we'll dive right into sort of the delay level analysis, and this is where we really took a couple of key delays and we investigated them in depth before later on in the presentation we'll kind of zoom out to some of the conclusions that we can draw at a greater network level. So there are kind of five main areas of analysis, and the first is platform waiting times, understanding how long people are waiting on the platforms, how many people are waiting on the platforms, are people still able to complete their journeys, and with sort of what reliability. What are the downline effects? So if there's a delay on one part of the network, how does that propagate through across within lines and across lines as well? And then finally, some basic work was done just to understand train trajectories. However, that's not going to be the focus of the presentation here. So first, starting with a delay timeline, this is kind of a familiar thing to many of us who have used the TTC. There'll be a Twitter post that goes out. There'll also usually be platform announcements at the same time. So no service in this case between St. George and Finch due to a signal problem. So this is most of line one. For those of you might not be as familiar with the TTC, line one is the primary line of the system and the busiest. And this is from one side of downtown through downtown all the way to the other side of the line. So now, about 15 minutes later, the TTC announces that there's still no service and that shuttle buses will be deployed. This is usually the TTC's approach to bridging disruptions, is to offer shuttle buses. They're deployed in a way that sort of depends a little bit on the delay and is often done with kind of dispatch and operator experience. This is sort of revised to 7 minutes later to just minor delays while we fix the signal problem. So trains are running, but there's still delays on the line. Minor delays on a shorter part. So this is just a subsection now of that original section of the line. So they've managed to resume service to the rest of it, but there are still minor delays on one part. And finally, about half an hour later, even on that last one part of the line, regular service has resumed. So overall, this was, as you can see, just under an hour, but it was at kind of the peak hour of the day in the morning on a weekday. So the first thing we're going to take a look at here is the wait times. And we've classified this as on the y-axis, you can see on that top graph that is the amount of time that passengers are waiting, and then on the x-axis that's sort of through time. So you can see I've marked these red lines here, and this will be consistent throughout the next few visualizations. These red lines indicate those 4 tweets you saw. So the first one is the initial delay when the delay was announced. The second one is when the delay was revised to minor delays rather than no service. The third one was when that delay period was shortened or the delay region was shortened, and then the final one is when the delay was resolved. And so on that last graph as well here below, we see that's the number of exiting passengers. So it's pretty clear to see here there's a major spike in passengers' wait times, even actually before the TTC has announced it, which indicates that there was the delay kind of started, and then it took the TTC a few minutes to get that information out to everyone. Likewise, when there's no service, there's also no terminating passengers. And so this actually does confirm that the train literally stopped moving during that time and no one was leaving the station because there was no one arriving at the station. So the same visualization is just shown for a couple other stations on the line here. So this is College Station, also downtown. And we wanted to just see how this varied across space. And then this is at Finch, right at the end of the line. So we do see there was clearly a bit of an earlier effect at some of the stations downtown compared to Finch, which saw those effects a little bit later on. So moving right along, kind of to the corollary of that is if people are waiting longer, how many people are waiting on the platform? And this was particularly striking to look at. Again, that green line here is when the delay started, and we see clearly a major spike going up in the amount of devices that are in each station. So stations are getting busy, but they're not actually all getting busy at the same rate. And we classified these into different geographic regions here. So you can see some of them are getting busier faster than the others. And I think this is an important result to show that that crowding isn't actually consistent across the line based on passenger arrivals. And then, of course, later on in the delay, it does decrease, with the exception of on some of the stations where the delay took longer to be resolved. So now moving on to the second question, sort of about reliability, are passengers reliable and able to complete their journey? Does it take much longer during a delay? How does it affect if you're going through delay area versus not going through the delay area? So this is the focus of this section. And you can see this little animation here is illustrating the way we look at this and the way we look at journey reliability more generally is we aggregate all of the devices traveling between a given pair of stations. So for example, Museum and St. Andrew, let's look at all the devices that started at Museum, ended at St. Andrew, and we'll see what is their mean or median travel time, what is the sort of standard deviation of that. And then we do that for each station pair. So these are not individual devices, they're actually kind of the aggregate of the devices that traveled on that route. So clearly there's a pretty major effect here where devices that were traversing the delay region on their journey saw a rather longer mean travel time. And this on the x-axis here is the mean travel time as a ratio. So compared to in sort of normal conditions, which we compared at a similar date and time when there were no reported disruptions, It took about 25% longer on average for a device to traverse the delay region than it did on a normal day. The sort of control group of devices that weren't traversing the delay region, maybe 1.03, so 3% longer, but well within the sort of realm of just variance. And we felt this was quite an important result to illustrate that actually the TTC as a whole, does have some isolation from the regions that are delayed, and there are still plenty of passengers that were able to complete their journey as scheduled, just perhaps not those who were trying to go through the delay region. Another visualization here, we're looking at downline effects, and this one is particularly fascinating to see. So we're looking at space on the x-axis here, so the stations on line 1 across the network, and then the time of day on the y-axis. And so you can see this is just on a control day with no disruption. The volume of people terminating at each station increases downtown. It increases right at the end of sort of just before 9 a.m. We can compare this to on a day when there was a disruption downtown, and you can see that number drops to almost 0 throughout the period of the disruption, with the exception of the Bloor-Yang station, which is an interchange station and therefore had passengers terminating as well from line 2. Likewise, the station wait times, we see there's generally a low station wait time on a control day. Change that to the day with a delay on it, and suddenly that wait time spikes enormously. This black just means that the median platform wait time was greater than 300 seconds, so over 5 minutes. And you can see this pretty consistently throughout, but you can also see how the delay was maybe resolved at slightly different times at different parts of the network. And I think this is a helpful view to sort of see how the delay propagated through the system. Likewise, just looking in the other direction here, we also see the same thing where line 1 in the direction of Vaughan, so that's the other direction going southbound, showed a longer time to resolve the long platform wait times on some of the stations at the north end, which indicates, we'll talk about the result later, but it does indicate that the Finch terminal often causes a bit of bottlenecking and propagates delays through the terminal. Moving right along to system level analysis. We took a look at what sort of correlations there were with the cause of delay, how that affected the results, if there were shuttle buses deployed or not, where the delay was located on the network or where the disruption originated from, what time of day it was, and there will also be we did look at delay literature as well, although I'm not going to focus on it as much on this presentation. So these very long graphs, admittedly, are for a longer delay that we compared. And this is an injury on the tracks delay where we looked at the median station wait times. And as you can see, there are actually, there's no passengers at all these stations in the center of the line were closed throughout this disruption. But on either side, you see spikes in passenger wait times, which we felt was quite interesting to see, to just see that there's sort of an asymmetrical movement of passengers at that time, and to understand where also there is a greater need to deploy shuttle buses or deploy extra transit services. And then here, this is an illustration of a delay that very clearly propagated downline. So these were just a minor delay to fix a mechanical problem, but even after this delay was marked as resolved, there were still a backlog of trains and an increased headway between a couple trains. They came down the network as the trains moved through the network. So this was particularly clear to see how, even while it started in one place at one time, that continued throughout the system for almost another 45 minutes. So just a bit of a summary, as I know I've been talking a lot. We saw when there was sort of a mechanical issue, a signal failure, local power outage or disruptive customer, there tended to be more cascading platform wait times because it was a shorter duration delay and the entire line wasn't stopped, but there would have been a increased headway between a couple of trains. So you'd see platform wait times increase for about 5 or 10 minutes, but this would sort of propagate down the line. These generally had less effects on the line's operation overall and affects journey times through the area, but at a lesser extent. Conversely, something like a fire, a larger power outage, an injury at the track level tended to cause a full or partial line stoppage for safety reasons, and the wait times grew sort of simultaneously across the network as those trains stopped moving. These delays were generally longer in duration and affected journey travel time significantly more across the network. These also tended to be the ones for which shuttle buses were deployed, just due to their longer duration and greater impact. So looking a little bit per region, we saw delays in the downtown region tended to have much more flow over effects between lines, and these were also less likely to use bus bridging. Wait times, however, were not as prolonged as on the outer network, as there are a number of other modes of transportation downtown, and people generally just sought alternate modes rather than waiting more than 8 to 10 minutes. Conversely, delays on the northern section of line 1 uniquely propagated back down the line due to bottlenecking at Finch. We saw that a lot, where if there was a northbound delay, then it would turn into a southbound delay. And that was an interesting result to see. We didn't see that to the same extent at the other terminals. Because in the other terminals, generally delays were fairly localized and were generally resolved with bus bridging if there was a major disruption. Finally, delays in and around transfer stations had the broadest impacts of them all, both in terms of wait time and ability for customers to complete their journeys. This perhaps isn't a surprise. After all, when a transfer station is affected, you're affecting 2 lines rather than 1, and there's not really any backup, even if a customer were to go to the other line. Beyond that, we're still looking into some of the sort of more specific impacts, but it was pretty clear that especially St. George and Bloor Young stations, which are the 2 busiest transfer stations, had the most profound impact on customer journey completion. And finally, just a couple of next steps. One of the very interesting sort of directions that could be taken is to help with strategic bus deployment. The data is basically reported live in terms of Wi-Fi connections. So looking at platform crowding and looking at platform wait times can be done live to understand sort of where is the greatest need. Perhaps there is less of a need in one direction or in one section of the line, and that can be done using data rather than just experience. And likely, and as well, better communications. The sort of looking at a customer level would allow the TTC to sort of better communicate and perhaps communicate more information more accurately to customers and help them sort of less feel like the delay is amorphous and it's just happening and there's no more information they have about it. For example, just here, a potential thing of the greater information that we could glean just from looking at the sort of waiting times and platform crowding across the line in space and time. That is all I have. I know that we'll have questions at the end of the hour, so I will pass it over to the next presenter, but thank you all for listening.
Yeah, thank you so much, Aidan. So we'll do it a little bit differently here. So if you have questions, please write them in the Q&A box at the bottom of the screen, and we'll have a little bit of time at the end of the session to answer questions on all 3 presentations. Thank you very much, Aidan.
Thanks so much.
Okay, so our next presentation is again by Diego, whom we've seen at the beginning of the day. So Diego is going to actually talk to us how he built on the method that he developed early on and he presented in the first presentation in which he developed like a more generalized framework for OD prediction for both normal operations and service disruptions and so on. So we've already introduced Diego, but just for those who are new, so Diego has a PhD in computer science and has been a postdoctoral fellow at TAL for the past couple of years. His research bridges between public transit and cutting-edge computational methods to build better and more reliable urban mobility in cities. And as mentioned before, Diego has a black belt in Brazilian Jiu-Jitsu. So he teaches actually at U of T the art of Jiu-Jitsu to students, and that's why we always have our meetings virtually. I don't really get too close to him. Okay, Diego, over to you.
Thank you very much. Can you see my screen?
Yes.
Okay, thank you, Professor. Okay, so this presentation links to my previous one, but proposes automating the OD matrix generation pipeline. So this research is still in its early stage, so the results are preliminary. Okay, So let's dive into our motivation and goals. Our objective is to create a data pipeline that can predict the OD matrix through Wi-Fi data automation. So this ensures that the tool is fit for tactical and operational decisions, mainly operational, and requires fewer manual interventions. So we already know from previous presentations that the Wi-Fi database provides a significant advantage due to its large amount of data and low latency, and enable us to develop robust and online data pipelines. So in my initial presentation, we estimated the OD matrix for a specific time, although we understand that the matrix changes throughout the day. So to capture these temporal variations, we plan to utilize a learning algorithm to generate it automatically instead of calculating on demand. Furthermore, we aim to ensure the data pipeline is scalable, so allowing us to increase the data input without redoing the model. Okay, so it is also important to know that the previous method is appropriate only for offline applications, but not adequate for operational applications. So to deal with this issue, we propose automating the 2 steps, so the step 3 and the step 4, which is the seed matrix generation and the balancing step. Okay, let's look at the previous pipeline with the notation for a better explanation. So the seed matrix contains the proportion of trips from each origin from the Wi-Fi database. So from practical experience, we know this matrix is updated over time, but we know it preserves some temporal patterns as well, such as morning and evening peaks, as Aidan showed in his presentation. In addition, the matrix also preserves the spatial information that also varies throughout the day. Yeah. So here the seed matrix is we see this Q letter. So displayed on the slide is the number of trips in a specific OD pair divided by the total amount of trips from that origin. So we can also interpret it as the percentage of trips. So it is a proxy of the true trip proportions. So if we store this matrix every, let's say, 15 minutes, for example, we will end up with a time series that can be used to train a learning algorithm. On the other hand, the balancing step required 2 vectors with the actual trip volumes of each origin and destination provided by the ABC gate count. So recalling, we are dealing with a tap-on-fare system. So with the ABC data, we know the origin of the trips, but not the destination. So that's why we need these 2 vectors to balance the matrix. Then we balance the matrix to minimize the difference. So remember the conditions for a balanced matrix, which is the sum of the origins. The difference between the sum of the origins and the sum of the destination needs to be 0. Okay. And once this difference is close to 0, we accept the matrix as balanced. So these are the second step that we are planning to automate in this process. So a learning algorithm can also learn, this step. So the question became how to represent the problem in a way that is learnable by this learning algorithm. Also, the second question is how to simplify some steps in the pipeline so we can get the balanced matrix automatically. Okay. Despite being the first step before running any learning algorithm, the data representation step is not trivial. So most machine learning and deep learning tools are designed to work with simple data types like images with a fixed structure and size like grids, or text or time series considered like line graphs or one-dimensional graph. So graphs can also be more complex with unordered nodes with dynamic neighbors as well. So for us in the transit field, represent a system network as a graph is natural. So as it accurately represents what we observe in the real world. However, this makes it difficult for many existing machine learning algorithms to work effectively, because storing data as a table, we are assuming that these instances are independent, which is not the case for graph data, and is not the case for a subway system as well. So like for us, this gap started a new branch in computer science in the 90s, but gained traction effectively in 2010. It's called geometric deep learning, or learning on graphs, which the goal is to generalize neural network models to non-Euclidean domains. So lately, new graph neural network designs have arisen to handle data represented by graphs. So I recommend reading the works of the papers of Petr Velichkovich and Michael Brownstein for more information. We know the subway system stores local network information at the origin node and from its neighborhood. So for example, a train delay will affect consecutive stations. Again, as Aidan showed in his presentation, or a disruption that causes unexpected backlog of passengers will also affect other stations. Thus, the algorithm must perform both information aggregation and propagation. If you represented the data as a grid matrix, where convolutional neural networks have reigned for many years, we would not preserve the spatial locality, as we would have to change the order of the rows and columns over time, or the nodes, yeah. Unlike convolutional neural networks, GNNs or graph neural networks can handle graphs with arbitrary size and complex topology. Okay. Another benefit of representing our system as a graph is to use the node and edge features to map a d-dimensional or n-dimensional embedding space, which is a low-dimensional space rather than the actual dimension of the graph. So that similar nodes in the graph are embedded close to each other. So the node features can range from graph properties to spatial information describing the station, for example. For example, we can store how many buses arrive each hour, or how many streetcars arrive at a certain bus stop close to the subway station. So we encode this information and insert it as features at the node or edge level. And depending on how we represent our problem, so for example, if it's a node task or an edge task, then we can increment the number of features accordingly. Okay, so the task we will perform is supervised learning on the graph nodes. So the output will be a graph of the subway system with the prediction of devices connected to the Wi-Fi network at step t+1. Like any supervised learning problem, we need to know what we consider labels. So in this case, the labels are the passenger volumes at each node or station within 60 minutes. Right now, we are training with Wi-Fi data only. So the result is the prediction will be a Wi-Fi graph. So the idea is to replace the Wi-Fi labels with the APC gate count in the future. Thus, the prediction will be directed to the actual passenger volume instead of a proxy. So this step will simplify the pipeline, as we will not need to balance the OD matrix. Also, we will not need the destination vector, as it will come out as a consequence of the element-wise multiplication of the seed matrix and the prediction of the origin vector predicted by the GNN. Although many graph algorithms keep transition matrices under the hood, which we can take advantage of, for the moment, we will only explore the ability to detect devices' passenger volume during peak hours. Yeah, so this is future work. In this presentation, we will focus on the pipeline 1, which is the prediction of the origin vector. Okay, so for pipeline 1, we are using the architecture published in the paper Diffusion Convolutional Recurrent Neural Network, so data-driven traffic forecasting from 2018. So DCRNN for short is a unique method that combines diffusion convolutional neural networks and recurrent neural networks to capture spatial temporal dependencies in the network. Its diffusion convolutional layers are inspired by how information diffuses in graph structures. Moreover, the recurrent neural networks component captures temporal dynamics in the data, make it highly accurate in predicting future conditions or future states. One significant difference between DCRNN and other graph neural networks is that most GNNs focus on either spatial or temporal modeling, but DCRNN combines both aspects effectively. For this implementation, we use the Python open source PyTorch geometric temporal library. In our example, we use 920 graphs. Yeah, so each graph is a snapshot of the volume of connected devices in a 60 minutes window. The period is from April 1st to August 31st, 2022, only business days. We map as a consecutive PM peaks from 3 p.m. to 7 p.m. In time series, the labels from previous graphs become features in the subsequent graphs. So we are using a lag of 4, which means we are storing on each node the previous 4 time steps. The training data set is split in 90% for training and test 10%. The learning rate is 0.01, and we are using Aidan optimizer. And the prediction task is node regression, which means Wi-Fi inflow devices. Okay, so preliminary results show that the algorithm did not correctly identify some peaks in some cases, but overall it captured their pattern. So this discrepancy is in some stations can occur for several reasons, including data issues in the Wi-Fi network. So this is the downtown transfer stations, Bloor-Young, St. George, Union Station, and Spadina. The next slide is we have selected some peripheral stations, that is those that are outside the region considered downtown. As we are testing demand diffusion in the evening peak, it is important to see how the algorithm predicts those stations' demand. The overlapping of the predictive data fits the true data better, but we still identify some discrepancies at the peaks. We are still investigating the best approach to minimize these effects. Just a short note is this algorithm is not optimized yet in the hyperparameters. So that's why we are only testing to see how the results are compared with the true data. Okay, there's certainly still, of course, much work to be done. So the next step is to improve the prediction results. And the idea is to exploit the features of the system that interconnect with the subway. So the features have the role of improving the expressiveness of the graph to separate the prediction subspace better. For example, mapping high-frequency routes, transit agencies that interface with the TTC, train stations, streetcars, and bus terminals. And we can model these variables as binary or map the volume of the vehicles, for example, planned for each hour. And for this, we just need, for example, to download the GTFS and calculate the number of vehicles planned for each bucket of 60 minutes. It would be even better if we could get the data on the volume of passengers arriving at the subway stations from different modes. But yeah, so it depends on partnerships. Okay, so an interesting result that I want to share is that we identify demand symmetries with clusters defined throughout the day. So the example on the slide shows the symmetry in the morning peak in the last week of September 2021. We calculated the cosine similarity and reduced the system to only stations with a score greater than 0.721 or a cosine of 45 degrees. So the edges that connect the stations are similar pairs, and the node size indicates the degree number, which is the sum of in degree and out degree. Visualizing demand symmetry helps us fine-tune the model, as we want the learning algorithm to be able to identify this pattern. So cosine similarity is fundamental in several graph neural network architectures, and is present is present in the attention mechanisms, such as graph attention neural networks, and the well-known transformers architecture. So the idea is to take advantage of this symmetry to help the algorithm to learn the patterns better. So to conclude our presentation, temporal graph neural network is an approach that aggregates spatial temporal information in a time series format and makes it possible to perform demand predictions. From our observation, the predictions capture the pattern of the series. However, we need to fine-tune the model to minimize the differences in amplitude and shift toward the true curve. So the pipeline model must still be calibrated in hyperparameters and optimized. So the model was not optimized in hyperparameters, but several open source libraries help in model calibration, for example, GraphGene. The subway system was represented as a homogeneous and static graph with discrete time. So we benefit from pre-coded architectures on GNN with a homogeneous graph that has discrete time. However, using the heterogeneous and dynamic graph and nodes and edges is recommended for a more reliable representation of the system. This topic is in our to-do list, and of course is more challenging. The results are promising and with several practical applications. So there are many practical uses for this framework. For example, we can predict demand in the event of a disruption in the system. So analyzing the predicted OD matrix can determine which origin destination pairs will be impacted the most, allowing for reallocation, for example, of shuttle buses during critical disruptions. Another useful application is for major events like the upcoming World Cup. It can track the increase in passenger volume at stations on match days and determine the most sensitive origin destination pairs to demand fluctuations. So this information can be used to make quick operational decisions. So yeah, so that's all. Thank you.
Great, very interesting work, Diego. Definitely a leap really over the previous sort of ad hoc method. So again, we're going to leave questions to the end of the session. So we're going to jump to the next presentation by Peter Lai. So Peter is a recent graduate from U of T's engineering science program with a passion for building innovative technology systems for public transit. For his undergrad thesis, Peter developed a modular and data-driven railway simulation software platform, which is what he's going to present right now. So in his spare time, Peter enjoys riding transit for fun and playing the game GeoGuessr, where he tries to pinpoint locations of random Google Street View images. So Peter, over to you.
Thank you, Amer. Can everyone see my screen and hear me okay?
Yes, we can.
All right, wonderful. Okay, so hello, everyone. Today I'll be speaking about my undergraduate thesis project on developing a modular data-driven mesoscopic simulation platform for stochastic railway networks. And this is called SPUR. And this was a project initially started by Willem when he was here at TEL. So first, a little bit of background. Why do we want to model railway networks? So around the world, railways serve as critical backbone of transporting people and goods efficiently both within and between cities. And over the years, railway networks are growing in complexity and scale. And when there are so many moving parts, when things do go wrong, the disruptions are costly. So we want to be able to optimize the planning, scheduling, and management of railway networks. And to help us do that, we harness the power of computing to model and simulate train movements under different operational scenarios. So the predominant approach of railway simulation in industry is what's referred to as microscopic, and an example of this would be OpenTrack, which some of you might be familiar with. And the main benefit of microscopic simulations is the high level of detail and accuracy, so that we can achieve the most realism by including every detailed information about the system, including the physical infrastructure, the signaling system, the vehicle physics, and also all the operational data. However, all of that detail has a cost, mainly the long computation times and also the complex setups and the large data requirements, which makes this not really suited for analysis at the network level. And also it's not particularly great for application in a real-time context. So on the other side, we have macroscopic models, which are also traditionally used. And they're like the opposite, where the network representation is very much abstracted. So we can get results really fast, but those results are limited to high-level aggregate statistics about the network level performance. So we can't really capture things like delay propagation very easily, for example. So between the two, we see trade-offs in speed and granularity. And this is where mesoscopic simulations come in to bridge this gap and combine the best of both worlds. The idea is that depending on what's relevant for the specific context of the simulation, we can represent certain aspects of the network at finer granularity while abstracting away other less relevant parts to save on the computational time. And this gives us useful results quickly without needing a whole lot of overhead in the model building process. And this is what lets us build larger networks with the same resources. So the application of mesoscopic models to railway traffic analysis have been very limited in the literature. A lot of models are really limited in scope and also specialized models for a specific purpose. And they're all proprietary, which makes them harder to access. So this is what motivated the development of SPUR. The research project had two objectives. The first one, of course, is to develop a novel mesoscopic simulation platform that is flexible and modular so that we can perform rapid prototyping and simulation and analyze railway networks of all sizes, which is very important. And the outcome of that was SPUR. And of course, naturally, the second objective was to validate SPUR's performance with respect to accuracy, flexibility, and speed. And we're doing this by building a real-world railway network within SPUR. We wanted to choose something that was decently sized and decently complex. And so for that purpose, the GO network, the GO train network in the Greater Toronto area was chosen. So what makes SPUR special? Well, it has all the key attributes of mesoscopic simulation that we talked about just now. But some of the key ones I want to highlight here are that it's modular. So we're modeling detail. We're modeling things in detail only where needed. It's agent-based, so we're tracking individual vehicles, so we can model the interactions between different vehicles. And that's what lets us model things like delay propagation. And it's also data-driven, so we are facilitating the calibration of parameters to real-world data with the architecture of SPUR. And finally, it's open source, so anyone could access it and extend it to build different custom modules to suit their specific simulation needs. So to help us achieve these attributes in the spirit of mesoscopic simulation, we follow two guiding principles in the design process: abstraction and simplification. So in abstraction, we are discretizing continuous infrastructure into individual components, and things like crossovers are abstracted to nodes, and signal blocks become discrete cells. Compared to the real world, we're also simplifying some things, including not having a centralized dispatch controller, so that we could have flexible track assignment logic kept entirely within the individual components at runtime, so that we can quickly swap different components in and out without affecting the rest of the network. We're also using dwell time distributions that are independent of the time of day. And we're currently assuming instant transition time between components, because practically that time is absorbed within the traversal times encoded in the components themselves. And finally, we're assuming also omnidirectional crossovers, but of course, a more complicated crossover with more restrictions could be easily implemented in the model as well. So in terms of the general architecture, the overall workflow essentially involves the interactions between two entities, trains and components. So the trains follow a set of components to traverse through, and that each component, the train requests the use of that component, and a component decides how long to hold the train for, based on different factors like the nominal traversal time of the component, or other trains using the component at the same time, or trains around the component. And at the end of that, it releases the train, and the train continues on to the next component, and that repeats. We also have the concept of jitter, which adds time-based randomness to the traversal times of the components, so that we can capture that stochasticity component and better model the real-world operational variances. And overall, the modular design of SPUR really enables flexible interchangeability of different components and different jitter types, so we can really customize the network really easily, and also change things really easily as well. So among the components that were developed, I want to highlight some key ones here. First one is the multi-block parallel track component, where it's one component consisting of multiple bidirectional parallel tracks, also spanning multiple signal blocks. And the trains move between signal blocks using a cellular automata model. And there's fully internal logic for train acceptance evaluation, and also basically managing the track assignment as well. And we also have the multi-track station component. So it's got multiple platforms, multiple tracks, and the tracks could be bypass tracks or tracks where trains can stop and perform boarding and lighting. And the dwell time of trains are sampled from probability distributions, which are fitted based on real world data. And finally, we have the block exclusive zone, which is really important. It allows us to model situations where we have multiple components, but we can only have one train occupying that entire section. And this is applicable for scenarios where we want to have bidirectional single track service. And there's logic for managing queuing of trains at the entrances to the zone to basically respect that infrastructure constraint. So now that we have the building blocks, it's time to assemble the actual network. So we built all the components in SPUR based on the track diagrams of the infrastructure. So we, using our principles of abstraction and simplification, we discretized the continuous infrastructure into these discrete components. We used train schedule and location data, both planned data and actual train movement logs on recorded on actual historic days. So we use that to build the routes and trips, of course, but also in particular, we use the actual train logs to fit dwell time distributions that are unique to each station. And we put all of those parameters into the components. And so from there, we have a set of input files to SPUR. All right, and now for the fun part, what does the results actually look like? So here we have an animation representing all the train movements that came out of SPUR, that came out of a simulation run. And this represents basically the normal service scenario where basically the vast majority of the trains are on time. So I'm going to play that for you now. And this goes for the entire day. So this is the morning rush hour. We can see here. And we have the midday service now, which a lot of service are primarily concentrated on the lakeshore lines. And then now we have the evening rush hour. and then now late night service. And all of this is simulated within SPUR. Okay, so that was pretty cool. Let me pause that. Cool, so that was pretty cool, but perhaps what's more useful is the ability to actually add delays to our network. So using the concept of jitter, we were able to add random delays for the morning peak scenario, and that's represented in the animation here. And this perhaps represents something like maybe a day with snowstorms. You can see all the trains with delays. They're carrying that the effects of the delay forward with them as they traverse the network and interact with other trains. So we can also look at the performance of the network using time distance diagrams. And so we're looking at here is the berry line in the southbound direction in the morning peak. And these are these scheduled train trajectories. So trains go from Allendale all the way to Union. And here we have the simulated train trajectories from SPUR. And if I flip back and forth, you can see that they are quite similar, quite close together. And these extra jagged parts in the simulated ones at the stations represent the explicit dwell times that we're simulating in SPUR, which are not encoded in the schedule. And we can also zoom in on a single train and look at how well the performance or how well the simulated trajectories match with the scheduled ones and also the actual recorded train trajectories on the represented day. And you can see the performance is very good. And now we can look at a different line, Lakeshore East, which is more complex. There are a lot more trips, and we're looking at both directions. And if I flip back and forth again, you can see the similarities still pretty good, but there's a bit more discrepancies. And if I look at a single train, so it turns out that a lot of those discrepancies are within the express trips. And this is because the traversal times between stations are encoded based on schedule, which assume local service. So there's a bit of a discrepancy in the actual speed of the trains. So this could be an area of future work where we can perhaps enable dynamic encoding of the traversal times based on the train speed, for example. Another cool thing we could do is to actually inject specific delays at a time and place that we want and observe the aftermath. So here what we're doing is we're injecting a delay at Clarkson Station on the Lakeshore West line. You'll see when it happens. So now there's the delay, there's a service disruption for 30 minutes where no trains could move through. And now once it's cleared, you can see the aftermath of the delay, and the trains are carrying the delay with them into the rest of the network as they interact with other trains. Cool. And of course, we can represent this with the time distance plots as well. You can see the trains responding to the disruption here and its aftermath. So to summarize, the key results we saw are really promising. We successfully replicated the GO train network in SPUR with all of the operational and infrastructure constraints. And the simulated performance matches the actual train logs quite well as well, with the difference being under just a minute for the vast majority of cases. We also retain the modular design of SPUR, so we can swap components in and out very easily. And of course, all of this was run really quickly. So the entire simulation for the full day and for the full network was run only in 14 seconds with more than 620 trips. So that is really promising. And with all of this, we have a lot of promising applications as well for SPUR. So we can now analyze large networks at the regional or even national level in a more granular manner than we could do before. We can integrate with other simulations like pedestrian flow and also surface transit. Because of SPUR's speed and granularity, a train service planner could quickly test ideas for different network and service configurations. And also SPUR could support simulation-based optimization. And this also opens the door for SPUR to be applied within a real-time disruption response context. So that is pretty much it. I will conclude by saying again that SPUR is open source. So here's the GitHub link. So feel free to check out the project, and comments and contributions are all welcome. So thank you very much.
Hey, thanks so much, Peter. Very, very exciting work. And again, yeah, acknowledgements really to Willem Klampenhauer, who was a postdoctoral fellow in our at TAL for about 3 years. Okay, so I know there have been some questions already answered. But again, reminder to everyone, if you have questions, you can put them in the Q&A box. I see some comments, but no questions. Okay, perhaps I can ask the first speaker, Aidan. Can you just elaborate a little bit on how the user waiting time at the platform level was measured? This is a very exciting study that it really, for the first time, as far as I know, is really looking at the user level delays, not really the train level delays. But this, of course, is enabled by the availability of the Wi-Fi data. So if Aidan can just a little bit elaborate on that.
Yeah, so the user waiting times at the platform level were really primarily measured through essentially just counting the difference between the association and disconnection times at the platform. We did limit that only to sort of devices that end up traveling to another point on the network. But we take a look at the first trace we get when a device enters the station, and then the first we get when it's on the platform level, and then the last we get when it's on the platform level. And when we plot that over time, we kind of see the variance. So that one is really just the difference. Platform crowding is sort of the same thing of just how many devices are loaded onto a given platform with all the hotspots on it at the same time.
Perfect, perfect.
Yeah.
So also, I think you wanted to talk a little bit about literature. So how do your results compare to other studies in terms of maybe the questions you were addressing?
Yeah, so there are a couple of other studies. It is pretty limited in terms of the literature, especially from sort of the passenger-facing viewpoint. There are several interesting studies sort of in the past decade, mostly out of Europe, that look at sort of like Wi-Fi or Bluetooth networks, some cellular networks, and then there's some that at least a little bit look at delays, but they're pretty unusual. So I would say the literature outcome was largely consistent. I mean, it definitely found in most cases that delays at the center of a network, whether that was whatever the network's design was, tended to be longer, tended to have more impact and disruption, which is not, all that surprising. It did seem to be pretty unique to the transit system, I will say, because a lot of the results had been developed for sort of the Paris Metro, for example, which just operates inherently in a different way. The Paris Metro, to my knowledge and to the study's knowledge, didn't really use bus bridging all that much. On the flip side, the TTC is one of the sort of foremost users of bus bridging to cover delays. So I would say there definitely needs to be more done at maybe a larger level and a comparative level to really get the more specific results than kind of just the geographic and time-based kind of results that it is worse in rush hour, it's worse at the center of the network, but those aren't perhaps shocking. Okay,
there's another question to you, but let's just move to another question to Peter. Which data sources do you use to validate and calibrate the simulation model in SPUR?
So for the GOAT network, we use the ATLS data from Metrolinx, which are basically the pretty granular train times at different time points throughout the network. So it's not just between stations, but also at specific points like between stations as well. So it's not just at stations. And so we use that to calibrate the traversal times between different components on the network. But the beauty of SPUR is that we can we don't have to use this data. We can also use other sources of data to calibrate all those traversal times and also the other parameters like the dwell time distributions. So yeah, if there's like a more detailed study on the dwell time probability distributions at different times of day, for example, at different stations, we can easily take that data and put it into SPUR.
Perfect. And I have a question to you, Diego. You mentioned in passing about the limitation of the CNN and how the method you're using overcomes some of those limitations. And I think you made a few remarks, but if you can just expand on this a little bit more.
Okay, thank you for the question. So in the machine learning field, the data representation is really important. As I mentioned, it's not a trivial task. So when you are modeling your problem, you need to decide how to represent your data, that you can extract the most information from that. So the convolutional neural networks is a good approach with when you have a grid. So the grid is when we have, for example, local shared information. And then when you use the future, like the convolutional future, then we can capture this information and the neighborhood information as well. But when we try to use the same approach on graphs, that is topologically is not the same. So we need to use the same idea, but trying to keep the invariance and the equivariance of the graph, which means that even if we have different graph shapes, we need to be able to convolute the graph and capture this information. So the future in convolutional neural networks is not able to perform well on graph shape. So that's why we have this new approach that works. Is a generalization of the convolutional neural networks for non-Euclidean shapes, like non-Euclidean distance, but is just to highlight the differences between graph neural networks and convolutional neural networks.
Okay, perfect. I think we are beyond our time. I think there was one question to Peter, to Aidan about, yeah, I think he answered it on the box. So, well, thank you so much to all presenters. Very exciting work on the use of Wi-Fi in the first two presentations, and also a very exciting tool. Congratulations to both you, Peter and Willem, on developing this exciting tool that has really a lot of promise. So thank you so much. And so this session is now over.